Our next section, 8.2, covers quite a bit. To start with, we'll be looking at events that are a little bit more complicated than what we've covered so far, so we'll be looking at unions and intersections of events. And then we'll introduce the complement of events, which is actually a really useful calculational tool for computing probabilities of given events. And last but not least, we'll end with just a short section on computing odds, which is an alternate way of expressing probabilities. So we'll jump straight into an example. We've got first example here. Consider again rolling a fair six-sided die. And the question is, what's the probability of rolling a number that is even and divisible by 3? And I'm going to be fairly formal here. So for starters, we've got our sample space. Sample space S is just all possible rolls of a six-sided die, 1, 2, 3, 4, 5, and 6. And let's give these events names. So, event of rolling an even number. Event of rolling an even number, let's call that A. And this event would of course be even numbers 2, 4, and 6. Remember, events are formally subsets of our sample space. And we also want to look at even and divisible by 3. So we've also got an event of rolling a number that is divisible by 3. We'll call this event B. And numbers that are divisible by 3 would be 3 and 6. But that's not what we're looking for either. We want both of them. We want even and divisible by 3. So we really want the intersection of these two events, right? We want the A union B. So this is what we really want. Event of rolling a number that is even and divisible by 3. Divisible by 3, sorry, running out of space to write there. Well, that's I'll call that F, but that's A intersect B. Right, for reasons, sometimes people just literally read this as A and B, because that's what intersection does, it gives you and. And what do we have? What's the intersect of these two sets? The intersection is just, common to both of them is just 6, right? And of course, you didn't have to go through this super formal process. You could have looked at this and said, which numbers here are even and divisible by 6? And you would have said, okay, well, it's just 6. But from here we can compute the probability, right? So the probability of this event F is the number of elements in F. So I'll write this as the number of elements in A intersect B. Over the number of elements in S. And we've just got one element in that set over the number of elements in S, 6. Again, not very surprising, right? We know the odds of rolling a 6, or sorry, the probability of rolling a 6 is 1/6. So there's intersections. So computing probabilities of intersections of events is fairly straightforward. You just compute the intersection of the events and find the probability. But let's do something a little bit more exciting. Let's do set unions. So what's the probability of rolling a number that is even or divisible by 3? So again, maybe I shouldn't have erased these, but we had A was the event of rolling an even number, so 2, 4, and 6. We had B was divisible by 3, so 3 and 6. Probability of rolling a number that's even or divisible by 3. Well, now we're looking at the union of these two events, right? So we'll let E be the union, the union of A and B. And this is of course 2, 3, 4, and 6. So if I'm computing the probability of E, well that's the probability of A union B, right? And that's of course the number of elements in A union B over the number of elements in S, which is, in this case, we've got 4 over 6, or 2/3. And again, for these fairly small events, when I can just read off what the union is and I've got these small sample spaces, you wouldn't have to do anything particularly formal here. You could just say which numbers in here are even and divisible by 3. Well, that's, even or divisible by 3. Well, that's 2, 3, 4, and 6. And because I've got 4 elements here, the probability is of course 4 over 6, or 2/3. But I want to I want to come up with a slightly more formal formula for this. So let's look back at this thing. The number of elements in A union B, what is that? Number of elements in A union B, well if you remember the number of elements in a union is the number of elements in A plus the number of elements in B minus the number of elements in their intersection. Okay? So what that means is that, let me get some more space here. What that means, if I plug this in here, that means that the probability of A union B is in fact the number of elements of A plus the number of elements of B minus the number of elements of A intersect B all over the number of elements in S. But in general, number of elements of A over number of elements of S is just the probability of event A. Number of elements of B over number of elements of S is the probability of event B. And then lastly, minus number of elements in A intersect B over number of elements in S, that's a probability of A intersect B. So in general, when you look at the union of two events, the probability of the union of two events can be given by this formula. Again, not super important to use in the very small examples we've just done, but when you have lots of possible outcomes, very large sample spaces, using this formal formula can be quite useful. And I want to make a note. A little bit of terminology here. Events A and B are called mutually exclusive. Mutually exclusive, or just disjoint, if they're the disjointed sets. Remember, events are actual sets, so they're mutually exclusive or disjoint if they're disjointed sets, meaning that they don't have any overlap. The intersection, A intersect B, is empty. So if A intersect B is empty, and you'll notice then in this case, in the mutually exclusive case, in this case, we have a nice shortcut for this formula. The probability of A or B is just the probability of A plus the probability of B minus, well, A intersect B is the empty set, so this is just minus 0. So in the mutually exclusive case between these two events, to find the probability of A or B, you just take the probability of A plus probability of B. So we'll do some more examples here. All right, so next example. Two people each randomly choose a number between 1 and 4, inclusive, so something but 1, 2, 3, or 4. And the question is, what's the probability that They're numbers they choose. Together these numbers sum to 3 or 5. So what's our sample space? Well, I tried to represent the sample space somewhat graphically here instead of strictly as a set, but first person chooses numbers 1 through 4, something between 1 and 4. Second person chooses a number between 1 and 4, and all the possible outcomes I've denoted it this way. Either first person chooses 1, second person chooses 1, or the first person, maybe I should go this way, this is the first person. First person chooses 1, second person chooses 2, or for another example, first person chooses 3, second person chooses 4. So the sample space is a set of all of these doubles that I have here. All right, so ranging between 1 and 4. Notice there's 16 elements total in this sample space. And what do we want to compute? So let's let A equals the event that they sum to 3. All right, so event of sum to 3. And how would that happen? Well, the only way they could sum to 3 is if one person chooses 2 and the other person chooses 1, right? So these two elements right here. So either 1, 2 or 2, 1. And B is the event of summing to 5. And how could that happen? Well, they could either choose 2 and 3 or each, or they could choose 1 and 4 each, so everything down this diagonal. Those are the only choices that sum to 5. So here we've got 1, 4, 2, 3, 3, 2, 4, 4, and 1. And you'll notice that these are mutually exclusive, right? These two sets don't have any overlap at all, so these are mutually exclusive. And therefore the probability of A or B, I want to find the union of these two events, the probability of A or B is just the probability of A plus the probability of B. Remember, I don't have to subtract off the probability of the intersection because there is no intersection, it's the empty set. And that means, well, what's the probability of A? It's 2 elements in A, so it's the number of elements in A, over the total number of elements in the sample space, which is 16. And probability of B is, there's 4 elements in B, over 16 total possible outcomes. So just adding these together now, we've got 6 over 16, or 3 over 8. Awesome. Let's do a slightly harder example. What's the probability that together they, let's go with that, well, let's erase all this first. What's the probability that they both choose the same number, that they both choose the same number, or that together they sum to less than, let's go with less than 5. Okay, so we need some events here. We've got 2 events. We want to take the union of these 2 events. So again, I'll let A be now, we'll call it same number. Event of same number. And I suppose we don't really have to look at the graphic here. This is sort of obvious. Either we're looking at 1, 1, or 2, 2, or 3, 3, or 4, 4. 1, 1, 2, 2, 3, 3, or 4, 4, running out of space here. That is, of course, this diagonal. I should try to erase the ones from the last example. So that's gone, and We'll pretend this is gone. Okay, so we're looking at everything in this diagonal. This is A. And what about B? B equals event of sum to strictly less than 5. Well, everything along this diagonal sums to 5, right? But everything in here, everything in here, all of those give me elements that sum to less than 5. So this set consists of everything in here. This event is everything in here. 1, 1, 1, 2, 1, 3. That's these entries. Then we've got 2, 1, and 2, 2. And then we've got 3, 1. And you'll notice that these are not mutually exclusive, right? These two sets have some overlap, and the intersection is these two elements right here, 1, 1, and 2, 2. So A intersect B is not empty. It's 1, 1, and 2, 2. So again, now the sets are pretty small. If you were to just work out A union B and count the number of elements in there, you wouldn't have a particularly hard time, but let's formally use our formula. So the probability of A or B is formally the probability of A plus the probability of B minus the probability of A and B, the intersection of A and B. So computing these, probability of A, we have 4 elements in A. So probability of A is 4 over 16. Probability of B, we have 6 elements in here, so this is 6 over 16. Again, the 16 is coming from the fact that there's 16 elements in the total sample space. Minus probability of A and B, or A intersect B, is there's 2 elements in here, so this is 2 over 16. The numerator here sums to 4 plus 6 minus 2 is 8. So this is 8 over 16, or exactly simplifies very nicely to just 1/2. Alright, so in a lot of these homework problems that you'll see, you can probably avoid using this very formal formula if you just want to count the elements. But it's nice to have this for examples where you have very large sample spaces, like possible hands dealt from a deck of cards, where you have absolutely huge numbers of possibilities and so on. We've talked about unions and intersections. Now we want to move on to complements of events, which are actually extremely useful in computing probabilities. And here's our definition. Given an event E, the complement of E relative to the sample space S, and we'll denote the complement of E using our complement symbol from set notation, so denoted E complement, is a set of all elements in S that are not in E. So the complement of an event is basically the opposite. It's all other possibilities. And we'll just do some calculations here. So hence, the probability of S occurring, well, S consists of two subspaces, or sorry, 2 subsets, is either the event E or not E. So E union E complement, and we know how to find probabilities of unions now. This is the probability of E plus the probability of E complement, and these are completely disjoint. You're either in event E or you're not in event E, so you're in E complement. So they're completely disjoint, so I don't have to subtract off the intersection or anything. And the probability of S occurring, the probability of everything in the whole sample space, is just 1. Alright, so it's this equality, this last equality here that's really important to us. So therefore, we have 2 really nice formulas. We can say probability of E complement, if I isolate this, is 1 minus the probability of E. And maybe even more useful is the probability of E. Probability of E is 1 minus the probability of E complement. And these are our two really useful formulas here when we're working with complements. So commit these to memory, or maybe even, I prefer this one to be honest, is that the probability of E and probability of E complement have to sum to 1. Therefore you have these two expressions. So just to start off with a very simple example. For example, if the probability, probability of rain, for example. So the probability of rain, which is the probability of the event we're looking at, what's the probability of rain? Suppose this is 0.55, then of course the probability of no rain. This would be the complement of this event. This is the probability of E complement. Sometimes you'll read this as not E, because it's the exact opposite. E complement is not E, if you want. And so if the probability of getting rain is 0.55, then the probability of no rain is of course going to be 0.45, but formally is it would formally be 1 minus 0.55 using our formula. So this is 0.45. Why? Well, because one of these two events have to occur. These two events are mutually exclusive, rain or no rain, and they're mutually exclusive. One of them has to occur, so they better sum up to 1. So if 1 is 0.55, then no rain must be 0.45. But this is a very simple example. Let's do something more complicated. Alright, so here's a slightly more complicated example, and I want to do an example like this where we have a very large sample space. So it's what is the probability of getting at least one diamond in a 5-card hand dealt from a standard 52-card deck. So of course I'm not going to write down the entire sample space, the sample space consisting of all possible 5-card hands dealt from a 52-card deck is absolutely huge, but notice that we don't really care about the actual sample space. When we're doing probability calculations, what we care about is how many elements are in the sample space. So the number of elements in the sample space would be, well, I'm choosing 5 cards from a 52-card deck. Order of the cards in my hand don't matter, so it's just it's 52, choose 5. Okay, so now let's look at some events. What event are we interested in? We're interested in the event of getting at least one diamond. So E is event of at least one diamond. And again, if you think in terms of combinations and whatnot, this actually isn't impossible. It's not too hard to think about how many different possible ways you can get at least one diamond. But what's much easier is to think about the complement of this. So E complement, if E is the event of at least one diamond, E complement would be the event of no diamonds at all, right? Event of no diamonds. And what I'm going to do is I'm going to compute the probability of E complement, because this is actually much easier. What's the probability of E complement? It would be the number of elements in E complement over the number of elements in S. That looks like a 5. And we already did the denominator. Number of elements in S is 52, choose 5. What about the number of elements in E complement? How many ways can I get no diamonds at all? Well, there's 13 diamonds among the 52 cards, right? So if I want no diamonds at all, I want to draw from the remaining 52 minus 13, which is 39 cards. So the question is, how many ways can I draw 5 cards from 39? So the number of elements in E complement is 39, choose 5. Right, because there's 39 non-diamond cards, so I'm choosing 5 cards from the non-diamond cards. I plugged both of these into a calculator. I got 575757 over 2598960, which is about, I rounded it to 4 decimal places, which is about 0.2215. Again, answer's rounded there. But of course, this is not the answer to the problem, because it's asking what's the probability of getting at least one diamond. It's asking what's the probability of E. We found the probability of not E, of E complement. Well, why are we basically done is because the probability of E is 1 minus the probability of not E. And I've already computed this piece, so the probability of E is just going to be 1 minus 0.2215, which is, which is 0.7785. Probably could have done that in my head, but. So there's the answer. Again, it's not impossible to just have proceeded directly from E, worked out how many elements are in E. You know enough about combinations and computing these things so far that that's doable, but it's much easier to find the number of elements in E complement and find the probability of E complement instead. And once you know the probability of E complement, you immediately know the probability of E using this nice relationship. So this is a really, really common way to proceed with these probability questions, and anytime you see something like this, it's these words here, it's at least. If you want at least one diamond, when you see these words, this sort of tips you off that this might be a good way to proceed, because the opposite of at least one is none. So if you see those words, maybe think about proceeding in this manner. So last up, just a little bit of extra terminology. Another way of expressing probabilities is odds. And odds are typically used in gaming or gambling situations where it's customary to discuss the odds of an event rather than the probability. Of course, they're both completely compatible with each other. If you know the probability, you know the odds, and if you know the odds, you know the probability. But for example, so when rolling a die, the probability of rolling, say for example, a 3, is we know the probability is probability of rolling a 3 is 1 over 6, 1/6. But the odds, when people talk about the odds are 1 to 5. Why are they 1 to 5? Well, again, think about gaming here, where you're thinking about winning or losing. There's 6 possible outcomes. In one outcome, you win. So maybe rolling a 3 is winning. In one outcome, you win. In 5 of them, you lose. So the odds of rolling a 3 are 1 to 5. One chance of winning, 5 chances of losing. Or, this is sometimes written as like this, 1 to 5. Alright, so this will be our definition. We'll just make a definition. We'll define odds in this way, though we'll actually define it as a fraction, but we'll make a mention of that. So, odds for E, this is our definition, we're defining this term, odds for E is a number that's equal to the probability of E over 1 minus the probability of E, or we know what this expression down there on the bottom is. That's the probability of not E, of E complement. Okay, and we also talk about odds against E. Is actually just the reciprocal. So odds against E is probability of not E over probability of E. And of course, I need some things to happen here. I can't ever divide by 0. So for this to make sense, probability of E over probability of not E, I need probability of E to not be 1. Because then this would be 0 and it would be divided by 0. And down here, this guy, I need the probability of E to not be 0. Otherwise, I'm dividing by 0. Okay, so this doesn't look like I mentioned when we were talking about 1 to 5 and so on. this looks like a ratio of two numbers, but you can easily convert this. So here we are expressing odds as a ratio in the form of A over B. But that ratio, when you're talking about odds, is usually written as, or read as A to B. Okay, so, but it's still written as A to B, or using this colon, A to B. The other thing I'll say is, you might, remember when you're plugging in these probabilities of events occurring, this might be like 0.45 or something. And you don't really want 0.45 over 0.55, and then your odds would be 0.45 to 2.45. So usually rescale. Usually scaled. So that A and B are whole numbers. That way when you talk about odds, you'll have nice whole numbers like 1 to 5. So there's our definition. These are our formulas for odds against E and odds for E. And they're just given by these very simple expressions. So we'll do an example or two. So a very simple example here. What are the odds of getting two heads when a single coin is tossed twice? We've looked at this experiment before. We know what our sample space is. You either get two heads, you get a heads and a tails, or you get a tails and a heads, or you get tails and tails. And the event in question is getting two heads, right? So there's only one way to do this. The event is getting two heads. And again, if you sort of understand the explanation for what odds are, then you could immediately just write down the answer. The odds are, well, there's one way to win and 3 ways to lose, so the odds would be 1 to 3. But we'll use our formula formally to compute the odds. The odds for E is the probability of E over the probability of not E, of E complement. So what's the probability of E? Probability of E occurring, there's one element in E, 4 elements in S, so 1 over 4. Over probability of not E, E complement. Well, E complement is everything else, right? It's all 3 of these guys. So probability of E complement is 3 over 4. How do you divide fractions? You flip them and multiply, right? So you instead of dividing by 3/4, you multiply by its reciprocal. So this is 1/4 times 3/4, or sorry, I didn't flip that guy. Times the reciprocal of this, 4/3, which is 1 over 3. Or you could write these odds mean, of course, this is or 1 to 3. By the way, odds against E, the formal formula is, of course, the reciprocal of this. It's P of not E over P of E. But once you've already computed the odds for E, you know immediately the odds against E. It's just the reciprocal of this expression. It's 3 over 1. Right, so or 3 to 1. So when computing odds, it's just use these formulas. Use these formulas here. Not really a whole lot to this. It's just an alternate way of expressing probability that we won't really be using. We'll be going back to the probability expressions we had before between 0 and 1. But odds are used so often in gaming that it's worth discussing, I think. But otherwise, we'll end with this example and we'll stop here.